Okay. Now, next thing, we will try to find the fields. As I said again, you can take the curl of A, find the B, and you can, with scalar potential, you can take the negative gradient of the scalar potential minus partial derivative of the vector potential with respect to time. You can find the electric field also. But let us try to find, instead of this, let us try to find the field strength tensor. Now, let us go back and write the four potential in a general forms. So V of alpha, depending on the proper time, theta x0 minus r0 tau, x0 is greater than r0, and therefore theta function is 1, delta function x minus r of tau square. So I evaluate this for potential. I find that the Lienard-Wiechert potentials. Now let me concentrate on the calculation of the field strength tensor f alpha beta. So elements of this are the del alpha a beta minus del beta a alpha. So let us try to calculate the elements. So let me say this is a beta, and try to calculate the del alpha a beta. So if you take the fourth derivative of this, you will obtain the following. V of beta of tau, x0 is greater than r0, so therefore you can act the derivative with respect to delta function over there. So this is 1 unity x minus r0 tau, and del of alpha, delta function of x minus r of tau square. So this will act to this delta function. So now let us call again this as a f. Then we have as a overall station here, what we have, del alpha, delta function of f. This could be written as del alpha acting on f times d over df delta function of f. So that is equal to del alpha of f d over d delta over df. Using the chain rule, that is equal to del alpha f d tau over df d over d tau delta f. So this is a simple chain rule. So let us try to calculate the elements. So df over d tau is given here, and we have to take the inverse of this quantity. Then we have to calculate here del alpha f. And f again, f is x minus r of tau. So basically so let me write here, del alpha of f is del alpha of x minus r of tau square, and that is equal to 2x alpha minus r of tau alpha. So that is the partial derivatives of the x minus r of tau with respect to the space and time. So this is that piece. And instead of d tau over df, you have the inverse of this. This is nothing but x minus r scalar product with v, and take the inverse of this. So in that presentation, it is tau, that is tau equal to tau 0. So we are not evaluating tau equal to tau 0 in general. So this expression will take the following form. So basically, del alpha, the delta function of f will be delta lambda f, that is equal to 2x alpha r of tau alpha times, so this piece is nothing but del alpha f. The other piece is d tau over df, d tau over df. So d tau over df is the inverse of this, but in general not evaluated at tau equal to tau 0. That is equal to what? So inverse of this is equal to 1 over minus 2 x minus r of tau scalar product with v. I think this is correct. This is d tau over df, d tau over df. So take the inverse of this, not evaluate tau equal to tau 0 in general. That becomes minus 1 over 2 x minus r of tau scalar product with v in 4 dimensional. And the leftover term will be d over d tau, d over d tau. Where is this d over d tau? D over d tau of delta f. Oh, here it is. So d over d tau delta f. So now let us try to evaluate the integral. So we have this, 2's cancel, we have minus 2, and put these things to the there and try to calculate the del alpha a beta. Del alpha a beta will be 2e d tau theta function x0 minus r0, and x0 is greater than r0, and v of beta, and this whole term put to some values. What are the some values? X alpha r alpha of tau, not tau 0 yet, divided by x r of tau dot v. The sign is minus, and the next d over d tau delta f. Now you can employ a integration by parts. So say this is a u and the other is dv, and call this is a dv. So integration by parts will give you the following: 2e d tau theta x0 minus r0 tau. So derivative of the, so basically that is nothing but u v times u minus du times v. So there's a minus sign, that will be positive. So that would be whole term will be in the derivative of d tau, because you call this a u, you call this a dv, then you have to take the derivative all of them with respect to the d tau, and that term will be what? Minus of this x alpha r alpha tau. So let me write as a just the difference, v beta depending on tau divided by x minus r of tau scalar product with v. So we have this times integral of this delta f plus uv from minus infinity to the plus infinity. This will be 0 because you have the delta function here and you have to satisfy the light cone condition. So if you look at the limits, this should be 0. It's not important. So basically we call this is a u, this is a dv. We are writing the minus du, so we have a minus minus that plus, and this is the d over d tau, this is the du terms, and that will be the v terms. And what is the v term? So that is delta f, delta f. So let me try to write this in here again. So del alpha a beta we are trying to calculate, and here I forget to write the factor of 2. There should be factor of 2, that should be cancelled. So we have e d tau d over d tau e times d tau and d over d tau, or let me write first the theta function, theta x0 r0 tau. Again, x0 is greater than r0. I am writing this all the times. Theta function is unity. D over d tau, and the rest is x minus r of tau of alpha, v of beta of tau divided by x v dot x minus r of tau times the delta f. What is the delta f? Delta f, remember, f is nothing but x minus r square, and delta f is whole term, okay, and this is nothing but the scalar product. So I made a mistake here. There's no 2 factor here, so sorry about this. No 2 factor at the moment, so there's a 2 here. Sorry about the 2 factors. So instead of delta f, you can write delta tau minus tau 0 divided by absolute value minus 2 x minus r dot product in 4 dimension v. So the rest of the term is delta tau minus tau 0 divided by magnitude of 2 x minus r of tau dot v in 4 dimension. Okay, so this piece is nothing but that delta f we calculated in the last hour. So basically now 2 factors are cancelled out. So if you take the, so here the delta function alone, if you take the integral through the d tau, you have to say instead of tau there's tau 0, and tau 0 is the retarded time. So if you take this integral, the result is very simple. Del alpha a beta is equal to e over x r of tau evaluated at tau 0 dot v, this term, times d over d tau, and this whole term evaluated at tau equal to tau 0, x minus r of tau alpha v of beta of tau divided by v dot x r of tau. All of the stuff have to be evaluated at tau equal to tau 0 because we have the delta function. So E is there, v dot x minus r of tau in here, that's scalar product, and d over d tau x minus r of alpha v beta divided by v dot x minus r, all of them evaluated at tau equal to tau 0, means that at retarded time, which is satisfying the light cone condition. So if you want to evaluate that the field strength tensor, that is nothing but del alpha a beta del beta a alpha. All you have to do, you should switch the indices, or you do the calculation again. So if you do the calculation again or switch the indices, put the, instead of alpha say beta, instead of beta say alpha, you replace the alpha and beta, you will obtain the field strength tensor as charge over x minus r of tau dot v d over d tau. First this piece x minus r of alpha, actually r is depending on tau, alpha v beta of tau minus x minus r of tau beta v of alpha tau divided by v dot x minus r of tau evaluated at tau equal to tau 0. Okay, so this is what kind of tensor? An anti-symmetric tensor. So you can replace the alpha and beta, you can get the negative of this if you replace this. So one should calculate this in order to find that the fields of the moving charge particle. So as you see that you have the derivatives here, that means that you will have the four velocities, space-times, and the derivatives with respect to the proper time. That means that you will have velocities and the velocity derivatives. So at this point, I am not going to calculate these elements. It's very messy, but I will show you how you can do, and I will just write the result. And using this, we can start the radiation from the moving charge particle. So for example, if you want to calculate the electric field, you have to write 01 I, 02 J, 03 K, and basically you have to evaluate those derivatives with respect to the proper time, and actually this should be the minus sign, so because these are the minus 01, 02, 03 are the minus fields, so minus EX, minus EY, minus EZ. So basically you need the tools. What tools you need? You need to know X minus R of tau of alpha. So that is R and Rn. So I know that the length of this is 0, and you need four velocities. You know the four velocities: gamma c, gamma v. For that, in order to calculate the elements of the field strength tensor, and you need the derivatives of the four velocities. This is complicated. Well, derivatives of the four velocities with respect to the proper time is c times gamma to the 4 beta dot. This is for time coordinate. For the space coordinate, c gamma square beta dot c gamma to the 4 beta dot. So you will need a derivative of this, that, and derivative of the other one. The derivative of the scalar product v dot x minus r is minus c square x minus r of alpha dv alpha over d tau. So this is messy, so you don't have to do work on. Okay, I will just give you the result. But basically here you are seeing that the derivatives of the velocities with respect to the proper time, that means that the acceleration terms. So you have to calculate the x components, y component, and z component of the electric field. So if you do this calculation, this messy calculation, you will end up the fields in the following form. So the fields will be the following. The electric field will be the following. The charge n minus beta gamma square 1 minus beta dot n cube r square evaluated at tau equal to tau 0, that is the retarded time, plus E over C n cross n minus beta cross beta dot, that is the acceleration term, divided by 1 minus beta dot n cube over r times. This is evaluated at tau equal to tau 0. This is a long expression. You don't have to derive this. And what does it tell? You have the terms depending on 1 over r square and depending on 1 over r. But if you look at carefully, 1 over r terms is related with the acceleration. This is the acceleration with the ordinary time, okay? So if you take the field strength tensor, if you plug this information, take the derivatives, do the whole algebra, you will obtain this. So that means that you are evaluating the radiation emitted at retarded time, and you are seeing that the electric field has two components. One is 1 over r squared, the other is 1 over r. And the 1 over r is more dominated, and if we are working for the accelerated fields, only important term will be the that. So from now on we will play this part. If we work on the field strength transformation of the electric field and magnetic fields a couple of weeks ago, and the part of your exam questions, using what we have the Boost matrices, field strength tensor, we find that the fields of the moving charge with constant velocity, if the charges are moving with constant velocity, you can use this part and verify our results we find a few weeks ago. Now I am not concentrate this part, I will concentrate with this radiation part. So basically, if there is no acceleration, beta dot is equal to 0, this whole stuff is 0, then you have the term only with constant velocities. We calculate that the fields of the moving charge particle with constant velocity, okay, using the Boost matrix and the transformation of the field strength tensor. But you can do this using this expression and you can find the identical results. So if you want to look at your book, there is a related section that proves that if the charge is moving constant velocity, the fields is identical, which we find using the Boost matrix and the field strength tensor, okay, which we did a couple of weeks ago. Then the next thing, if you know that the electric field, you can calculate the B field, and that is mutually orthogonal to the electric field. So we know that that is true for the radiating fields. They are one-to-one because we are using the Gaussian units, okay? So we change the units. Now the next thing, using this, you can study the radiation. Let us start the radiation, then stop. From now on, we will work on this piece and the radiation until the end of the course. So let us work on what is going on for the radiation emitted at low velocities. So if V over C is small, you can ignore the all beta terms, and if the charge is accelerating, so if the charge is accelerating but beta V over C is small, the situation is the following. So take this part as a radiating field due to the acceleration, because only term has the acceleration here in that term, and tell all the betas as 0, okay, this 0, this 0, okay. Then the electric field of the accelerated charge particle will be E over C n cross beta is equal to 0 n cross beta dot divided by R. So if this is the electric field due to the accelerating charge particle, you can immediately calculate that the power. What tool you need? The pointing vector S. S is C over 4 pi E cross B. But I know that the B is n cross E. B is n cross E. So double cross product rule tells you that that is related with what? This is E charge. This is equal to E over 4 pi. So E square along n. So E is nothing but the field of the accelerated charge particle. B is the field of the accelerated charge particle. This is along the direction of n. So let us remember the double cross product rule. So E dot E along n minus E dot n along E. So basically radiating fields are transverse, okay? So propagation of the radiation and the electric field and P's are orthogonal to each other, okay? So this is the pointing vector. Then you can write that the power emitted per Soldt angle, that will be what? C over 4 pi, that will be real part of this, so that will be that. So that is, remember, that is equal to what? Power emitted per Soldt angle was equal to, if you remember that the definition, that is equal to what? R n dot S. So that was the power emitted per Soldt angle. So S dot n times R. So that is E over 4 pi, no, C over 4 pi. C over 4 pi. So power emitted per Soldt angle related with what? Real part of the n dot S. S is the pointing vector. So n dot E cross H times R square. R square. Okay. So basically, you need what? Square of the electric field times the R square. So that will be the following: C over 4 pi R square, and the square of the amplitude square of the electric field will be what? E square over C square over r square and cross beta dot square. So power emitted per solid angle is in that form. So cancel the C's, and as you see that the r square cancel naturally. That is independent of the reduced power emitted per solid angle, and we obtain E square over 4 pi c and cross V dot over c square. So take the c square there. Power emitted per solid angle will be, this is c square, there's a c here, that will be E square over 4 pi over c cube and cross acceleration. So basically the situation is the following. Charge is accelerating, and that is the point we are looking at the radiation. So we have the fields, accelerated fields are perpendicular to the propagation direction. So basically n cross v dot, so if this is the angle theta, n cross v dot is nothing but n unit vector v dot sine theta, but n dot v is perpendicular to the n. This is nothing but E square over 4 pi c cube acceleration magnitude square times sine square theta. So you are seeing a very nice result, like a dipole radiation. If you know that the acceleration of the charge, you have the pattern of what? Dipole. So if the charge is accelerating in arbitrary direction, the radiation pattern is something like this. So this is the angle. So along the acceleration direction, no radiation, the angle is 0. The maximum radiation is at the 90 degrees. We will see that if the acceleration is relativistic, this situation will be changed. And if you integrate this through the all solid angles, you will obtain the total power. So sine square theta integrated through the solid angles, sine theta d theta d phi, you will obtain, I think, 8 pi over 3. Anyway, the total power will be 2 over 3 E square c cube times the square of the acceleration. So this is a very important formula. This is called a Larmor formula. If you know that the acceleration, then you know that the total emitted power. So for example, in the exam questions, there was an electromagnetic wave interacting with the charge. So then the electric field component of the charge will oscillate the charge. In that question, you should calculate that the electric dipole moment of the oscillating charge. But here, you can do the same thing that will be related with the Thomson scattering. You can find that the acceleration of the electron, oscillating electron, if there is an electromagnetic field, if there is a charge, what happens? Charge will start to oscillate due to the electric field of the electromagnetic wave. So you can write that the force on the charge, that is E times electric field. Then you know that the acceleration, then you know that the total power emitted from the oscillating charge. So this will be the, we will study this, that will be the, we will study this in the Thomson scattering. So this is a Larmor formula for non-relativistic. And you can write this formula dividing by mass and multiplying by mass in the following form also: 2 over 3 E square over m square c cube, and that is nothing but m square v dot square, and that is equal to 2 over 3 E square m square c cube dp over dt dot product by itself. So total emitted power could be written in terms of the acceleration, also could be expressed in terms of the force. If you apply a force in order to accelerate the charge, you can find the total emitted radiation. So next thing, we will generalize to the relativistic. So we will write this as a for momentum, derivative of for momentum. So this is the Larmor formula that is non-relativistic. If you know that the acceleration of the charge, you know that the total emitted power. So fields, as you see, that depending on 1 over r, therefore the total power per solid angle does not depend on r, because r square coming from that power per solid angle and 1 over r square cancel each other. So you can see that the radiation elsewhere, because anywhere, because there is no any loss of the radiation. This is r square terms and r square terms cancel out. So if the charge is accelerating, the pattern is the dipole, and this total emitted power could be written by the total applied force. Next time we will study this by generalizing to the relativistically. Okay.